we have a common type of furnace, which is known as electric arc furnace. And in this furnace, an electric arc is generated between the electrodes, and generally these electrodes are made up of carbon. So you can see this is the construction of your furnace. So at the bottom of this furnace, you place your ingots, and then these are electrodes which are made up of carbon, and then you supply current between the electrodes and the metal scrap placed here. So it results in the generation of arc between the tips of these carbon electrodes, and this arc is of very high temperature, and enormous amount of heat is liberated on the surface of your scrap metal, and which causes the melting of the material. And at the bottom of this furnace there is a tilting mechanism. It is just like a drawbar type of mechanism, so this can control the tilting of this whole furnace, and the metal which is melted here inside the cavity, it can be easily poured into the ladle. So that ladle you can carry, and then you can pour the metal out of it into the mold cavity. So this is an electric arc furnace, and it is generally associated with the production of alloy steels, tool steel, and stainless steels. So for melting of steels material, this particular furnace is widely used in the foundries. So after this, we have to understand that how much amount of heat is required to heat the metal, and to convert it into the molten form from the solidified form. So the heat energy required to melt the material to a sufficient casting temperature is generally the sum of three components. So the first component is the heat to rise the temperature to the melting point. So how you can calculate this heat? So this is calculated with the help of this component, which is your rho v. Rho v is your mass. So mc delta T, if you remember it from your thermodynamics, that the heat which is required to raise the temperature to the melting point, it can be calculated with the help of mc delta T. So here this C is your CS, and it is the weight specific heat for the solid metal in joules per gram centigrade. And then the second component is the heat of fusion to convert it from the solid to the liquid. So here you have to you require the heat to convert the one form of material into another form. So here you are interested to convert the solid form into the liquid form, and it can be calculated with the help of m into delta H. So here H is your heat of the fusion. And lastly, there is a heat which is required to raise the molten metal to the desired temperature for pouring. So when you apply the heat, the temperature rises, and your solidified metal converts into the liquid form, because here you have achieved the melting temperature. And even then, at the melting, just achieving the melting temperature is not enough, or it is not good to pour the metal just at the melting point, because if you try to pour the metal at just at the melting point, then it can solidified in the middle of the pouring. So it is better to increase the temperature somewhat higher than the melting point, and for increasing that temperature require the heat. So that will be calculated with the help of this mc delta T again. So here that C is your CL. So CL is your heat of the liquid, specific heat for the liquid metal, and this TP is the pouring temperature, which is greater than the melting point. So this is the total amount of heat which is required to heat the metal and to make it suitable for the casting process. Then after this, a very important aspect to understand, which is the pouring of metal into the die cavity. And this particular stage has some important points that you should all understand. The first point is the pouring temperature. So this temperature, pouring temperature, is the temperature of the molten metal as it is introduced into the mold. So I told you that it should be greater than the melting point. Then we have another term called superheat. That superheat is the difference between the temperature at pouring and the temperature at which freezing begins. So it is basically the melting point of a pure metal of the liquid temperature of an alloy. And so your metal should be heated into the superheated range, and this amount of heat must be removed from the molten poured metal to initiate the solidification. So that amount of heat which you have applied extra, this is called the superheat, and it should be removed from the molten metal to initiate or to start the solidification process. And then we have the pouring rate. So very important term is your pouring rate, and it refers to the volumetric rate at which the molten metal is poured into the mold cavity. So this pouring rate is very important factor for a satisfactory casting process. And if this rate is too slow, suppose if the rate is very less, then metal will chill and freeze before filling the cavity, and your process will not be completed, and you will have a casting of undesired shape and size. However, if you keep this pouring rate very high, so it will result in the development of turbulence in the molten metal, which is itself a serious problem, as the turbulence accelerates the formation of metal oxides and also results in the mold erosion. So that turbulence is in inside any fluid flow. You know that turbulence is basically abrupt change in the direction and the velocity of the fluid. So it results in the introduction, you can say, the trapment of atmospheric gases inside the molten metal, and which results in the corrosion and oxidation of metal. So the formation of metal oxide will be higher, and it also result too much of the pouring rate also results in the mold erosion. So mold erosion will cause the problem, further problem in the flow of the molten material, and it will also result in the defected cast product. And so the type of flow, that whether it is a laminar flow or it is a turbulence flow, in most of the casting application, this fluid flow, molten fluid flow, should be in the laminar flow. And that type of fluid flow can be determined by a very known, you can say, known number, which is known as the Reynolds number. You might have studied in the fluid mechanics, and this is calculated with the help of this simple formula, which is equals to rho vd, and rho vd upon mu. So rho is the density, v is the velocity, and the d is the diameter of your runner and the gating system, and mu is your kinematic viscosity. And so you all know that if this Reynolds number is less than 2000, then your flow is of laminar type. Otherwise, if it is greater than 4000, then the flow will be turbulent flow. So before pouring the molten metal into the die cavity, you must have to calculate this Reynolds number in order to anticipate the type of the fluid flow into the mold cavity. So if you like the video, then please subscribe to my channel, share it with your friends, and don't forget to hit the bell icon for the latest updates. Thanks for watching my videos.